Today, we are going to look at some one dimensional steady state heat conduction problems involving heat generation. We will consider one dimensional steady state heat conduction with heat generation first in an infinite slab and then in an infinitely long solid cylinder. So, let us look at the first situation. In this sketch here, I am showing an infinite slab of width 2b, all right, and I specify to you that in this slab heat is being generated at a uniform rate q bar. Everywhere in this slab heat is being generated at the uniform rate q bar. We would like to know the steady state temperature distribution in this slab. The distribution obviously is going to be such that I will get a larger temperature in the center, a lower temperature at the edges, and we want to find an equation to this temperature distribution which is shown here. All right. Now, first of all, let us formulate the problem. That means, let us put down the differential equation, let us put down the boundary conditions of the problem. In order to put down the differential equation, let us look at our general differential equation. Our general differential equation, if k is a constant, is k for a general situation is k multiplied by d2t dx squared plus d2t dy squared plus d2t dz squared plus q bar is equal to rho Cp dt dt. That is our general differential equation which we have derived earlier, where in the general case being one where variations may occur in x, y, z and there may be an unsteady state also. Now, in this particular case we know that because it is an infinite slab, there is variation only along the width v and therefore, which we call the direction x. Therefore, there will be no variation in the y direction, there will be no variation in the z direction. All right. We also know that there is a steady state, therefore, the term dt dt is equal to 0. So, in this case the differential equation for which we have to solve reduces to the form d2t dx squared is equal to minus q bar by k. Notice now, I have gone from the partial differential to the ordinary differential, because we have only variation in one direction, the x direction, and there is no variation with time. So, we have to solve this second order differential equation subject to the boundary conditions which we have on the two faces. What are the two faces of the slab? Let us go back and look at the slab. The two faces of the slab are x is equal to b, x is equal to b and x is equal to minus b. At both these faces we specify that there is a heat transfer coefficient h. At both these faces we specify that there is a heat transfer coefficient h and that the fluid outside is at a temperature T f. The fluid outside to which heat is being lost is at a temperature T f. All right. So, the boundary conditions on the two faces, we have a boundary condition of a heat transfer coefficient, and in mathematical terms the boundary conditions will become, on the face x is equal to b, we will get, on the face x is equal to b, we will get minus k dt dx at x equal to b is equal to h into T at x equal to b minus T f. All right. The heat being transported by conduction inside the slab at x equal to b is equal to the heat being lost by convection at the face x equal to b to the surroundings. And similarly, at x equal to minus b, minus k dt dx at x equal to minus b is equal to h into T f minus t at x is equal to minus b. Notice the interchange, this is now T f minus t at x equal to minus b, because the heat flow by conduction as given by Fourier's law is always in the positive direction. Okay. So, this we call the formulation of the problem. We have stated the differential equation and we have stated the two boundary conditions at x equal to b and at x is equal to minus b. Now, we have to solve this, and solving it is a straightforward thing, just a second order differential equation. I integrate it twice. If I integrate it twice, I will get, integrating the differential equation twice, first I will get dt dx, the first integration will give me dt dx is equal to minus q bar by k x plus c 1, and the next integration will give me t is equal to minus q bar by k x squared by 2 plus c 1 x plus c 2. That is the general solution. Now, I use my boundary conditions which I have got. I have two constants C 1 and C 2, two boundary conditions at x equal to b and x equal to minus b. Put those two boundary conditions in, solve for C 1 and C 2, which I will not do on the board here, I will leave it for you to do. But if you do that, you will get the solution for the temperature distribution, and one gets the temperature distribution to be the following. You get T is equal to T f plus q bar by 2 k b squared minus x squared plus q bar b by h. That is what you get for the temperature distribution in the solid, and that is the equation for the temperature distribution which I showed right at the beginning. That is the equation for the temperature distribution of the which I showed right at the beginning, that is this temperature distribution. It is a parabolic temperature distribution that we get. Obviously, the maximum occurs at the center, and if you solve for, in order to obtain the maximum value T max at the center, you put x equal to 0. So, you will get T max is equal to T f plus q bar b into b by 2 k plus 1 by h. So, that is the maximum temperature that occurs within the solid, within the infinite slab at the center line. So, this is the solution to the problem that we have got. Now, we will solve the same problem for an infinitely long solid cylinder. Suppose I have an infinitely long solid cylinder of radius capital R, all right, and heat is being generated in it uniformly at the rate q bar. I ask myself, find the temperature distribution in this solid cylinder and find the expression for the maximum temperature, which will obviously again occur at the center line, that is at R equal to 0. So, in this case, if you go to the differential equation in cylindrical coordinates, I am not going to put that down, but go back to the differential equation which we had for constant k in cylindrical coordinates, all right. In that differential equation, note that t is only a function of r, t is not a function of theta, t is not a function of z. Note also that it is a steady state problem. So, there is no dt dt term. If you do all that, then you will end up with this second order ordinary differential equation t varying with r, and the boundary conditions now are, one boundary condition is at the center line, this is the symmetry condition. Because we have symmetry at r equal to 0, dt dr must be equal to 0. The other condition is at the face, the round face r equal to r, circular face, minus k dt dr at r equal to r is equal to h t at r equal to r minus T f. Solve this, that means again like we did for the slab, integrate this twice, put in the two boundary conditions and obtain the two constants of integration, which I will skip this time, because it is very similar to what we did for the slab. Now, if you do that, if you integrate the differential equation and use the boundary conditions, we get the solution to be T minus T f is equal to q bar by 4 k into r squared minus r squared, close the bracket, plus q bar r by 2 h. This is the equation for the temperature distribution inside the solid cylinder. And the maximum temperature again, if you wish to find that out, put small r equal to 0, in which case this term goes to 0 and we get T max is equal to T f plus q bar r by 2 multiplied by r by 2 k plus 1 by h. That is the maximum temperature which occurs at the center line r equal to 0. So, these are two simple one dimensional problems with uniform heat generation, which we have solved for the case of a slab, an infinite slab of width 2b, and for an infinitely long solid cylinder. We could solve similar problems, one dimensional problems also. For instance, on your own, I suggest try to solve the problem for a long hollow solid cylinder, a hollow cylinder, all right, inner radius r I, outer radius r o, heat being generated uniformly in it. Assume that there is a heat transfer coefficient h on both the surfaces at r equal to r I, r equal to r o, and the surrounding fluid temperature is T f both inside and outside. Solve the problem. You will again set up the same differential equation, you will integrate it twice, but because of the change boundary conditions, you will get different values for the constants of the integration. So, that is a problem you can do on your own, a problem of a long hollow cylinder, or take the problem of the sphere. I suggest you do that on your own. Take a solid sphere, assume of radius capital R, assume that heat is being generated uniformly in it at the rate q bar, find the temperature distribution in that solid sphere. Do that on your own. There should be no difficulty in doing that problem as well. All right. Now, let us do a numerical example, just to illustrate ideas and to substitute into the formula that we have just derived. Here is the problem that I would like you to do, and let me just dictate it, so that you can take it down. The problem is concerned with nuclear fission, a nuclear fuel rod in which fission is taking place, and it is as follows. It says a nuclear fuel element is in the form of a long solid cylindrical rod, parenthesis K thermal conductivity equal to 0.85 watts per meter Kelvin, close the parenthesis, of diameter 14 millimeters. It generates heat at the uniform rate of 0.45 multiplied by 10 to the power of 8 watts per meter cubed, because of nuclear fission. The heat is transferred to pressurized cooling water at 300 degrees centigrade, and the surface heat transfer coefficient is 4500 watts per meter squared Kelvin. Calculate the maximum temperature in the fuel rod in the steady state. I repeat, calculate the maximum temperature in the fuel rod in the steady state. This is the problem. It is a straightforward substitution into what we have done. Notice, in a pressurized heavy water reactor, we have uranium, natural uranium a form of uranium oxide is the fuel. The thermal conductivity is about 0.85. These are values which are close to real values, and heat is being generated at this rate because of the fission. Neutrons are striking and breaking up the uranium atom. So, we are generating heat by fission at the rate given. Obviously, because of heat being generated, temperatures rise, the heat is transferred, but we get a temperature distribution inside the fuel rod. Find that temperature distribution and particularly find the maximum temperature in the fuel rod. That is the problem. All right. Now, let us do it. So, this is, let me just sketch things a little. Let us say this is our fuel rod. Let me just draw a rough sketch. All right, this is the fuel rod. Some uranium oxide, some form of uranium oxide. The conductivity of this fuel rod is given to be 0.85. So, let us put that down. K is equal to 0.85 watts per meter Kelvin, and the heat is being generated uniformly in this bar. Q bar is equal to 0.45 multiplied by 10 to the power of 8 watts per meter cubed. All right. We are given that the radius of the rod R is equal to 7 millimeters. That is the radius of the rod. The heat transfer coefficient at the surface H is equal to 4500 watts per meter squared Kelvin, and the temperature Tf of the pressurized cooling water flowing on the outside is 300 degrees centigrade. All right. Find T max. That is the problem. It is a straightforward problem. There is really just a matter of substitution. So, T max is equal to, going back to the solution which we had a moment ago, I am just substituting into it. T max is equal to T f plus Q bar R by 2 into R by 2 K plus 1 by H. That is what we got from the solution for the solid cylinder. So, we get, substituting, we will get 300 plus 0.45 multiplied by 10 to the power of 8 multiplied by the radius, that is 7 into 10 to the minus 3 meters, divided by 2, the whole thing multiplied by 7 into 10 to the minus 3 divided by 2 multiplied by 0.85 plus 1 upon 4500, which is the heat transfer coefficient. All right. And if we do the calculation, we will get this is equal to 983.5 degrees centigrade. T max is equal to 983.5. This is the maximum temperature occurring on the center line of the rod. All right. This is the maximum temperature of the center line of the rod. This is what we are interested in finding. This temperature must not exceed the safe value specified for that fuel rod. If it does, then we must either cool more effectively, or we should not generate so much heat by fission, whatever it is. Either you will have to lower the value of Q bar, or increase the value of H, or decrease the value of T f. In some way you have got to do something. If you do not, if this 983.5 is above a safe value for the fuel rod, because you do not want that fuel rod to melt, you want it to be safe, but just keep on giving out heat by fission. All right, now let us take up a small extension of this problem. The extension is as follows. I ask you, what is the change in the maximum temperature? This is what I want you to do further. Say, what is the change in T max? What will be the change in T max if the fuel element is encapsulated in a thin metal cladding of thickness 0.5 mm. All right. The uranium oxide is inside a thin metal cladding of thickness 0.5. What will be the change in T max if I give you, if this is the additional information? Neglect, in order to simplify the calculation, I will say neglect thermal resistance of the cladding. In order to simplify the calculation, neglect thermal resistance of the cladding. I want you to do this on your own. You should find, if you do the problem on your own, you should get the answer T max decreases by 2.3 degrees centigrade. That is the answer you should get if you do the calculation on your own. So, we have done the calculation for a fuel rod alone. Now, I am saying, suppose the fuel rod is surrounded by an encapsulation, which is a metal cladding 0.5 millimeter thick. Neglect the thermal resistance of the metal cladding, how much would T max change? And the answer is T max should decrease by 2.3 degrees centigrade. I want you to do this on your own. All right. Now, let us now move on to some other situations. We have considered some situations of heat generation. Now, I want to move on to situations in which temperature is no more just a steady state. That is, we want to move on to more general situations in which temperature varies with time. So, we want to now consider some problems of the unsteady state. We want to move on to unsteady state heat conduction. In general, if I have a general problem in unsteady state conduction, T will be a function of x, y, z and time, all right, or T will be a function of r, theta, z and time if I am working in cylindrical coordinate. That is a general situation in unsteady state conduction. And if that were the case, if it is a general situation and I wanted to solve for it, then you have already seen the general differential equation which I put down a moment ago, but I will just show it again. You recall we had put down the general differential equation for heat conduction, when we did the heat generation problem. This is our general differential equation. So, if t is a function of x, y, z and time, this will be our differential equation with the d2t dy square, d2t dz square, dt dt term all being retained. This would be our general differential equation. Okay. So, obviously, life is going to be more complicated the moment we go to the unsteady state, because not only will t vary with space, t will also vary with time. So, straight away you are going to have a situation in which t is going to be a function of at least one space variable and the time variable. So, straight away you will have a partial differential equation. Now, a major simplification is obtained in conduction problems if one assumes that temperature variations within the body are negligible. It is possible to conceive of situations where these temperature variations within the body are negligible and temperature is only a function of time. For instance, suppose the body, solid body that we are talking about, is undergoing an unsteady state. Suppose that solid body has a very high thermal conductivity. Obviously, temperature variations within that body are always going to be very small. You understand? So, a major simplification is possible if we assume that temperature variations within the body are negligible. That is, we first take up for consideration bodies with negligible internal temperature gradients. And what is the mathematical simplification as a result? The mathematical simplification is that the temperature T is then only a function of time. All right. So, first now in considering unsteady state situations of heat conduction, let us first consider those situations in which we can neglect internal temperature gradients. So, temperature is only going to be a function of time. All right. Let me illustrate now. Let us derive the differential equation for this situation. Bodies with negligible internal temperature gradients. Let us say I have some solid body, could be any shape, and let us say its volume is V, its surface area is A. At the surface, this body during the unsteady state loses heat to a surrounding fluid which is at a temperature T f, and the heat transfer coefficient is H. Let us say the body is initially at a temperature T 0, some uniform temperature T 0. I suddenly put it in surroundings at a temperature T f, and there is a heat transfer coefficient H at the surface. If T 0 is greater than T f, then the body is going to cool. If T 0 is less than T f, the body is going to heat up. If we neglect internal temperature gradients, the temperature will only be a function of time. We would like to find that functional dependence. How does temperature vary with time for such a general situation? Let me first sketch the temperature distribution before we solve for it. For this case, suppose I have a, let me just sketch it. This is the type of graph we are likely to get. If we were to plot temperature of the body against time, all right, and starting at time t equal to 0, then if we were to sketch the temperature of the body is going to change like this. It is going to go on decreasing, and it is going to asymptotically it will approach the value of T f as it keeps on cooling down. All right, this is T f. This is the initial temperature T 0. So, the body is initially at a temperature T 0. When it is immersed in surroundings at a temperature T f, then it cools down and it is going to cool in this fashion. We would like to find an equation for this line, this cooling curve. We would like to find that equation. That is the problem. Okay. Now, let us formulate it first. Let us formulate the problem. If I apply the first law to the solid body, what will I get? At any instant of time, applying the first law of thermodynamics to the solid body, it is a closed system. Okay. At any instant of time during the cooling process, at any instant of time during the unsteady state process, at any instant of time, we will get rate of change of energy of the solid body rho Cp V dt dt. Rho into V is the mass, Cp is the specific heat, dt is the rate of change of temperature with respect to time. This is the rate of change of energy. This must be equal to the rate at which heat is transferred to the body, which is H into A into Tf minus T. Mind you, if the body is cooling, then this will be a negative number, and this will also be automatic, dt will also be negative because the body is cooling. So, the gradient will always be negative. So, this will be the applicable differential equation, which we have to solve applying the first law. Let us make the substitution theta is equal to T minus Tf. I make the substitution theta is equal to T minus Tf. What do I get if I make the substitution? If I make the substitution theta equal to T minus Tf, I will get the differential equation becomes rho Cp V d theta dt is equal to minus H A theta. That is my differential equation. If I integrate this differential equation once, integrating to get the solution and using the initial condition, what is my initial condition? So, solving this differential equation and using the initial condition, time t equal to 0, capital T is equal to T 0 or theta is equal to T 0 minus T f, which I will call as theta 0, all right. Using the initial condition at time t equal to 0, theta equal to theta 0, we will get the solution to the problem to be, it's a straightforward first order differential equation. We will get the solution to the problem to be theta by theta 0 is equal to e to the power of minus h a t divided by rho Cp V. That is the answer. Okay. It is an exponential decay, theta by theta 0 goes on exponentially decaying e to the minus term, or instead of theta I can write T minus Tf, instead of theta 0 I will get T 0 minus Tf, and this gives me the temperature distribution in terms of T. Okay. So, as I said, the moment we introduce the notion of negligible internal temperature gradients, we do not have to worry about temperature as a function of x, y, z or r theta z inside the body. We just say temperature is a function of time, get a first order differential equation and the solution is there. Now, whatever be the shape, suppose the shape is a cylinder, then for A and V I will put in the values for a cylinder. Suppose the shape under consideration is a slab, I will put in the values of A and V for a slab, whatever they are, you understand. So, that I will get appropriate solutions for the particular shapes that I am dealing with. But here I have a general solution for any shape, because I have made a very major simplification by assuming that there are that the temperature gradients inside the body are negligible. But this we cannot always do. We can do it in some situations, and if we do, well, we have got a solution, the problem is over. But suppose we cannot neglect internal temperature gradients, which is very often the case. So, now we go on to consider bodies in which internal temperature gradients cannot be neglected. We go on to such situations. And first of all, we will look at unsteady state heat conduction in an infinite slab. Again, I will again as usual look at an infinite slab. So, the problem now which we wish to solve is the following. We have an infinite slab of width 2b, all right, an infinite slab of width 2b, all right, initially at a temperature T naught. It is initially at a temperature T naught. This slab is suddenly put into surroundings which are at a temperature T f, and the heat transfer coefficient at the surface on both the surfaces, this face x equal to b and this face x equal to minus b, the heat transfer coefficient on both the surfaces is h on this face as well as this face. H on both surfaces, T f the temperature of the fluid on both sides. All right. T f the temperature of the surfaces the fluid on both sides. So, the slab is going to cool, and we would like to find equations for the temperature distribution in the slab as it is shown cooling. It could be heating up also. If I show T 0 less than T f here, the slab would heat up. It does not matter. We can solve, the solution we obtain will be general enough for both cases. It could be the case of heating, cooling or heating, but it is the same physical situation. Initial temperature T 0, surrounding fluid temperature T f, heat transfer coefficient on both faces h. Find the temperature distribution as a function of x and time. Find T as a function of x and time inside this slab. That is the problem. T as a function of x and time inside the slab. Now, just to sketch it, this is how the temperature is going to cool. Initially, it is uniform at T 0, then the temperature is going to look something like this, then after a little while it is going to look something like this, then something like this, and if you wait long enough as time t tends to infinity, finally you are going to get a uniform temperature in the slab at time t equal to infinity, which is equal to T f. The slab will attain the temperature of the surroundings, right. So, we want equations for these temperature distributions as a function of x and time. Now, again like earlier, let us first put down the differential equation and let us put down the boundary conditions, and in this case also the initial condition of the problem. What is our differential equation? Just to repeat again, the differential equation which we have, which is to be solved, is the general differential equation to be solved is k d2t dx squared plus d2t dy squared plus d2t dz squared plus q bar is equal to rho Cp dt dt. That is our general differential equation. In this case, temperature is only a function of x, and time. So, d2t dy squared will be 0, d2t dz squared will be 0, and there is no heat generation in this case. Therefore, q bar will be 0. So, in this particular case, the differential equation will reduce to the form k d2t dx squared is equal to rho Cp dt dt. That is our differential equation in this case. Rho k into d2t dx squared is equal to rho Cp dt dt. Okay. Now, the differential equation which we have got, we can also express it in the form alpha into d2t dx squared is equal to dt dt, alpha being nothing but k by rho Cp. I think I have mentioned it to you last time. Alpha equal to k by rho Cp is, alpha is the thermal diffusivity of the material. Like the previous case of negligible internal temperature gradients, let us again define theta equal to T minus Tf. Okay. Same way as earlier, theta is the temperature above the ambient temperature, the ambient is the benchmark. In which case, if I make this substitution, the differential equation will become alpha into d2 theta dx squared is equal to d theta dt. So, this is our differential equation in terms of theta as the variable rather than t as the variable. Okay. Now, if this is our differential equation, then we have to solve it subject to the conditions of the problem. This is an unsteady state situation. So, we must have an initial condition and we must have boundary condition. The initial condition that we have is at time t equal to 0, capital T is equal to T 0. I have stated that, or in terms of theta, theta is equal to T 0 minus T f, which is nothing but theta 0, which we will call as theta 0. Instead of writing T 0 minus T f, we will write this as theta 0. That is our initial condition. Now, boundary conditions. We have two faces for the slab, x equal to b, x equal to minus b. Now, one thing we can recognize in this case is we have a symmetrical situation about x is equal to 0. All right. So, we can also solve the problem in the positive domain, that is from x equal to 0 to x equal to b, and take account of symmetry and use the appropriate boundary condition which we will get due to symmetry at x is equal to 0. So, that is what we will do in this case. We will say d theta dx at x equal to 0 is equal to 0 by symmetry, because symmetry requires that the temperature distribution in the positive half and the negative half, one must be the mirror image of the other. That is the requirement of symmetry for x equal to 0. If you want one to be the mirror image of the other, then obviously d theta dx at x equal to 0 must be equal to 0. All right. The other boundary condition is at x equal to b, and there we will get our usual condition by Fourier's law minus k d theta dx at x equal to b is equal to h into theta at x equal to b. Now, instead of writing the full condition like we wrote earlier, if we write it in terms of t, we would get minus k, let me put that down. In terms of t, it would have been minus k, the partial of t with respect to x at x equal to b is equal to h at t x equal to b minus T f. That is the boundary condition in terms of t. If I put the substitution theta equal to t minus T f, this boundary condition will reduce to the form minus k d theta dx at x equal to b is equal to h into theta at x equal to b. Okay. So, this is my boundary condition for the problem. So, we will solve the problem only in the positive half, that is from x equal to 0 to x equal to b, and we will use the symmetry condition at x equal to 0. Okay. So, this is the full statement now of the problem. We have got the differential equation, we have got the initial condition, we have got the boundary condition. Now, in this class, we will not solve this differential equation. This is a partial differential equation. So, obviously, it calls for a more sophisticated technique to solve it. We will not do that in the class, but I am just going to give you the solution directly as has been obtained. The solution for this partial differential equation is obtained by what is called the separation of variables method. This is the method used for obtaining the solution to the problem, and the solution is obtained in the form of a convergent series. Finally, we get the solution in the form of a convergent series. So, I am skipping the solution method here, because that is not required in this class, how we get the solution, how we solve the partial differential equation. I am simply saying that the partial differential equation which we have stated, subject to the initial and boundary conditions which we have stated, after solution, when it is solved, we get this as the solution, and this is the solution. Theta by theta naught is equal to 2 into the summation, this is an infinite series, n equal to 1 to infinity sin lambda n b upon lambda n b plus sin lambda n b cosine lambda n b e to the power minus lambda n squared alpha t cosine lambda n x, where lambda 1, lambda 2, lambda n up to lambda n etcetera are called the eigenvalues and are the roots of the equation. Cotangent lambda b is equal to lambda k by h. This is the solution to the problem. It is a convergent series of this form with the lambdas which are called as eigenvalues being given by the equation cotangent lambda b equal to lambda k by h, which in turn is equal to lambda b divided by h b by k. Now, let me just write this solution out a little, so that you get a feel for it. Let us say we write it out a few terms of the solution. We get theta by theta naught, let me write the solution, put lambda equal to 1, lambda equal to 2 etcetera, so that you see the solution. So, you will get 2 multiplied by the first term is obtained by putting lambda 1 b. So, we will get sine of lambda 1 b divided by lambda 1 b plus sine of lambda 1 b cosine of lambda 1 b into e to the power minus lambda 1 squared alpha t cosine of lambda 1 x. That is the first term of the series. The next term of the series will be plus sine lambda 2 b divided by lambda 2 b plus sine of lambda 2 b cosine of lambda 2 b e to the power of minus lambda 2 squared alpha t cosine of lambda 2 x plus so on. Then finally, we will get an nth term, and we can go on. If we had actually to do the numerical work, we would have to put in values of lambda 1, lambda 2, lambda 3 etcetera, and we will find that slowly it will go on converging, and we will stop after a certain number of terms if we are doing some numerical solution for a given problem. The lambda 1, lambda 2 etcetera, as I said, are given, are called the eigenvalues of the problem and are obtained by are also available in the literature. But let me just graphically illustrate what I mean by them. The solution to the lambda 1s is cotangent lambda b is equal to lambda b divided by h b by k. All right. That is what we are solving for. Now, in order to visualize what we are solving here, it is like this. Let us say this is the x axis, y axis, this is the x axis. We are effectively saying the following. Let me draw. The cotangent if I plot the left hand side, which is nothing but the cotangent, I will get something like this. The cotangent starts from plus infinity and goes to minus infinity, all right, periodically, like this. This is the cotangent term, and the right hand side is lambda b. So, on the x axis I have lambda b, and on the I am plotting the function. This is the cotangent lambda b which I have plotted. This is cotangent lambda b that I have plotted, and lambda b divided by h b by k. H b by k is some constant. So, if I plot that, I will get a straight line with a certain slope like this, and these are the values of lambda 1 b, lambda 2 b, lambda 3 b, etc. So, this is lambda 1 b, this is lambda 2 b, this is lambda 3 b. The intersection of the cotangent curves with the curve lambda b divided by h b by k gives me the values of lambda 1 b, lambda 2 b, lambda 3 b, etc. You follow? So, this is the solution that we have got for the one dimensional unsteady state temperature distribution in the slab. Now, next time, this is the temperature distribution and these are the eigenvalues. Now, next time we will talk a little bit more about this solution and how it is presented in graphical form.